Hi everyone, welcome back. In this lesson, we're going to build on what we did in the previous tutorial where we had an agent, right, following the mouse here. We programmed this agent using vectors. If you haven't watched part one, please go and do this and come back. What we're going to do in the second part is we're going to build on this and we're going to create a group of agents. Another ways to think about this would be to we could call this a particle system. In other words, we're going to have lots of moving objects on the screen that are all going to share the same behavior. And we're going to talk about different strategies we can use to manipulate these objects, to manage them over time. And ultimately, we're going to make their movement interesting using Perlin noise, kind of tying it back to what we covered last week. So let's just jump right in. Now we are going to go and so what I did is I made a copy of the previous example that we just developed, and we're going to further clean it up a little bit. So in this example, we're not going to use the follow the mouse behavior. So because we're not going to use it, I'm just going to take that code out. So just we don't have other things to kind of get confused by. So we're going to take that behavior out, and I'm going to even just delete that function. You can always refer to it in the other example. And we're also going to delete this commented out code that I forgot to remove in the previous video. The reason for that, again, I'm trying to keep the code clean and focused on what it is that we're trying to cover. So let's talk about creating a group of agents. Well, all that means is that, we're going to, instead of having just one agent variable, one agent object, we want to have 10, 50, 100, maybe 1,000 even. So we're going to need a place to park them. We're going to need a place to put all of our variables, and the ideal structure for that is an array. So instead of having agent here as a single variable, we're going to make an array. And just so we don't get confused, we're going to call our array, let's call it group. Okay, so we're going to have a group of agents. So this is a syntax for creating the array in P5, right? We just say group equals array. And in setup, we're going to go and create a whole bunch of agent objects and then push them to the end of this empty array we just created. So let's create a for loop here to help us with that. We're going to repeat 100 times using I as our counter. And then inside here, we're going to create an agent. So I'm adding let here because I deleted the global variable agent. So we're going to define it again. Let's change the starting coordinates maybe for this to the center of the window for now. And we are going to take these agents and we are going to push them at the end of our group. So push is a function of the JavaScript array class, and it allows us to add objects at the end of the array. So let's just throw these at one after the other. And by the time we're done, we're going to have 100 agent objects in this group. Now in draw, what we need to do is say we want to move and render all of these agents. So we're going to place this code inside a for loop as well. So let's write a for loop here. We are going to count from 0 to group.length in steps of 1. Okay. And then we will put inside our curly brackets, wrong key, we will put move and render agent. Now we're using agent here because previously that was our global variable, and I like being able to just use the variable name, not group bracket I. So let's just do something like this. We're going to say agent equals group bracket I. Okay, so grab an agent. So that's just a preference. I don't like to use this syntax with the brackets. I find it gets messy. So at the start of the loop, we're just going to take one of the agents from the array, right? Group bracket I is one of the agents, put it into its own variable, temporary variable called agent, and then we're going to move and render that agent. And that's going to look something like this. Now, this is not very exciting because they're all bunched on top of each other. So let's give them a bit of a push as well when they start off. So we could do this any number of places. We're going to do it inside create agent maybe. So this is where we create the agent. And the reason I'm going to put it in create agent, I'll come back to that in a minute. But we could also do this over here, right? After we've created our agent variable. It's the same object we're manipulating. The difference is where do I choose to manipulate it. So we're going to go inside the function that is responsible for creating our object in the first place. And after this has been created, we're going to create a little vector. Let's call it a nudge, okay? And this is just going to be a random vector, could point in any direction. An easy way to create a random vector is we could say p5.vector.random2d. Okay, so get a random vector. And we could even scale that a little bit, because otherwise this is going to be a little bit small. So why don't we scale it a bit? We're gonna multiply it by, let's say, a random number between 2 and 4. Okay, just to have some variation. Not nudge t, just nudge. And then we'll treat that as a force. Remember, previous example, we had forces, like following the mouse. We could apply a vector to our object. That's a kind of like a push or a force. So we'll say apply force temp. That's the agent we just made, the temp, and give it a nudge. And then we're going to return that object back. Okay. So give our new guy a nudge and hits play. Let's see what that looks like. Okay, so now we got something that looks like a bit of a ring. So they've changed. Obviously, they had a little bit of motion. And the reason they still all look bunched up like this is that in our previous simulation, we had the friction quite low, which means the number is low, but the actual friction is high. So let's increase that number a little bit to see what happens. So now they're going a little further. Right? We can go 0.9 here if we wanted to. Oh, they're going a little further. We can actually get like pretty close to 1, pretty close to no friction as this example. Let's go to like 98. And now they actually have a chance to like float a little bit. We'll go to 99, right? If we had no friction whatsoever, like let's say we had 1 here, right? They would just fly away, right? Nothing stopping them. So we're gonna just slowly reduce this a little bit, and just so that there's something slowing them down, right? So now we're getting a cool spread. All right. And if you want to experiment with that, this might be a good time to really quickly bring in like a little interface, a little slider. Remember from previous weeks, we're going to grab that GUI. So I'm copying the script here, the script tag. We're going to go really quickly into our index. Boom, put down that GUI into the head tag here. Save the index. And now we can create a user interface. Let's jump back into our script. And we are going to make... I like to create a global variable for the GUI in case down the road we need to refer to it. Let's say GUI equals new GUI. And then what we need is we need to put this friction variable inside an object. So we'll call that object settings. That makes sense to me. We will create friction, which is quite high right now. And then now when we want to refer to the friction, we will simply have to say settings.friction. Where is that? Friction. We will now have to say settings.friction. We're putting it inside an object because this is just how that GUI likes to operate. And once we've done this, we can add a particular setting to our GUI, and we'll give it a range. So maybe we'll get a range from like, I don't know, 0.8 to 1. Okay? Just so we can tinker a little bit. And now we will have this this friction setting. There's a mistake somewhere. Let's track it down. Random 2D, undefined. Okay. Don't know what happened there. I guess I accidentally deleted the word vector. Just my bad. Okay. And now we can affect the amount of friction that's in our sketch. Right? And we'll be able to play with this down the road, just so we have something that we can use to control the friction. And you can also enter in numbers manually, by the way, if you want to. So anyways. Okay, so we've added a GUI. And also I want to point out, again, we're in a series about generative systems. Everything is an opportunity for some kind of drawing machine, right? So here I have this cluster of agents that just explode from the center. What if even we just move the background to setup, right? Just something really simple, like, oh, cool. All of a sudden we're getting like a shape that emerges, right? Maybe we change the stroke to be semi-translucent a little bit, just to kind of like make it look different, right? So everything is an opportunity for some kind of drawing machine, some kind of drawing system. I just want to point that out, and I'll keep doing that in this lesson. Okay? Let's move the background back to draw and get rid of this opacity so we can see what we're doing. Okay. Awesome. So now that we have a structure where we can add more agents to our sketch, right? We can add agents at the beginning. We could also just keep adding agents over time if we wanted to, right? So for instance, we could say if mouse is pressed, right? If we press the mouse, we're just going to kind of squeeze in some extra agents in that system over there. And let's use these lines of code here where we're creating the agent. And instead of width over 2 and height over 2, we're going to use mouse X and mouse Y so that the agents appear from the location of the mouse cursor. So this is going to create some new agents whenever the mouse is pressed, right? So we can add more in there if we want to. Pretty neat. So all we're doing, right, is just adding more agents into this array. And then we have a little core loop inside draw that just goes through the whole list, does the same thing with all agent, right? Move and render them. And we can add them at the beginning. We can add them later on as we choose. Now we're going to get to a point where things are going to be like a little cluttered, right? We can play with our friction if we want. We're going to get to a point where it's getting a little bit busy in here. We do need a little bit of friction. Things are getting a little bit cluttered. So it's nice to be able to also get rid of agents over time. Okay. There's lots of ways we could try to program this. We might say when an agent leaves the screen, maybe we just get rid of it, right? If we can't even see it, why bother moving and rendering it? There could be all kinds of different conditions for us to get rid of an agent. For simplicity in this example, we're going to add the concept of a lifespan to our agents. In other words, we're going to kind of give them some HP, right? Some hit points if you play video games. And every frame that they survive in this environment, they're going to slowly lose some HP, some life. And when their life reaches 0, then it's very sad, but we're going to get rid of that agent. So first thing is we need to give each agent some amount of life or life force. So all that's going to mean really is just we're going to add a variable inside our agent object. So just like they have a position, a velocity, and acceleration, now they're also going to have some life. Okay, so it's just a number. We could give every agent the same amount of life, maybe like 100, or just to mix it up a bit, some of them will have longer lifespans, just so it's not always the same. So somewhere between 100 to 120. Okay? And we can go back and change those numbers later. So they have a pretty short life. And the in move, okay, we could do this. This is the other place that makes sense to do that. Sadly, we can't stop aging. So every time an agent moves, they also get a little tired, and we just subtract 1 from their life. Okay? And at some point, that life is going to reach 0. And we could keep an eye on that over here in our main kind of animation loop, right, inside draw. And we could say, okay, if agent.life, and just to be safe, in case we ever take chunks of life that are bigger than 0, we'll say if ever gets less than 0, okay, or we can say less or equal. It's not really important to be precise here. Time to get rid of that agent. Okay, so we could just get rid of them. So what does it mean to get rid of an object in our program? It simply means we need to remove it from the group. If we take it out of the array, then it might as well not exist. It might as well be gone. It's not going to get moved or rendered. It's gone. Okay? Now in JavaScript, the way we remove objects from arrays is we need to know their index. So we know that. We have the variable I here, so we know the index of that agent. And we use the splice command on the array. So we'll say group.splice. We'll give the index of the object we want to remove. And splice can actually remove a whole sequence of objects, but in this case, we're going to say just remove 1 object. Okay. The second parameter is how many objects do we want to cut starting at index I, and we just want to remove the 1. Okay. We could put 10 here, but then we would be killing 10 objects at once. This is not what we need. So splice with the index of the thing we want to take out, and how many things we want to take out from that index, just 1. Now we're going to run the sketch. And over time, right? As their life runs out, the agents will disappear. They're going to do their thing, and then eventually they're going to go away. So this allows us to have this kind of living system where we can keep adding elements to it, but eventually they're gonna get replaced with new ones. Now you're gonna notice something here. What happens when they disappear? We get this weird sort of like flickering happening, and this is not normal. This is not supposed to happen. The reason this happens is actually we have to be very careful when we iterate over an array, right? We iterate over a sequence of objects while at the same time, once in a while, removing something from that array. And the reason we're having an issue here is because we are iterating forward through the array. So if you think about it, when we remove an object from the array, right, after we're done, we take something out, the array shrinks, okay? Which means the next object that we're going to be visiting is actually not the one we meant to visit next before, because like the array has shrunk. It's now in the same spot as the one we just removed. So we're going to end up skipping objects as we delete stuff. And this is why we get this weird glitch. Okay. How do we work around this? It's very easy. Instead of counting forward through the array, we're going to count backwards. If we start at the end, it doesn't matter if we remove objects as we go through. We've already visited what comes after them, right? Or what comes before in that case. So even though the array will keep shrinking as we remove objects, if we start from the end, we're not going to miss anything. So starting from the end just means shifting a little bit how we frame this loop. We are going to say, instead of counting from 0, we're going to start from I equals group.length -1. So we're going to start from the last index. We're going to repeat as long as I is greater or equal to 0. Okay. And we are going to decrease in increment of 1. So we're doing the same thing, we're just counting from the end. So if we do this, then the weird little visual glitches are gone. Okay. So this is important if you ever have a situation where you're iterating through an array, and then somewhere inside the loop, you're also going to tinker with the array. Maybe you're going to remove stuff from it. Maybe you're going to add stuff to it. It's always a good idea to count backwards. And then this way, you're not going to have any kind of funny behaviors. You're not going to accidentally miss somebody if the array is changing while you're iterating. Okay? So very important, but small but important detail. And again, I want to point out everything is just like an opportunity for a drawing machine. Like let's put our background right back into setup, right? And then maybe one cool thing we could do is we could map the life of these squares. We could map it to the alpha value, right? So when we render an agent, maybe we'll set a white stroke, but then we will map that agent's life, which we saw up here could be as high as 120. You know, if they were one of the lucky ones, we're going to map it to a number between 0 and 255. In other words, the less, you know, the image alpha will decrease as the life runs out of that agent. You know, how poetic. So very neat. We can even turn this into like a little drawing tool. Maybe we comment out the cluster at the beginning, right? Now we have nothing, and we can use our mouse cursor to get agents to emerge from different places. Anyways, everything can be turned into a system, can be turned into something else. Let's bring these guys back here. And maybe we'll do that again. So I'm going to leave a background inside setup here. And yeah, if we leave the fade here, you can see it's kind of cool how basically as the agent's life runs out, they also fade out. So that could be kind of nice. Let's leave that in there for now. Okay. Or, you know, maybe we'll temporarily take it out just because it makes things maybe a little bit harder to see on the recording. All right. So now that we have a group of agents, we've created basically this particle system that we can animate. We have a basic framework for motion and all that. We have a simple behavior here. We just give them a nudge when they start. Let's talk about maybe creating some more interesting motion using Perlin noise, which we covered last week. Now, last week we used a strategy for the Perlin noise where we simply took 2 different points along a single dimension of Perlin noise and used that as an X and Y coordinate. Today we're going to apply Perlin noise in the context of this position, velocity, acceleration, vector-based motion that we've been talking about. So what we're going to do is we're going to create what's called a Perlin field of vectors. Okay? And that's going to become very clear what it is as soon as we illustrate it. This also ties in with the grid from the very first lesson that we had. So let me demonstrate what I mean. First, we're going to do some two-dimensional Perlin noise real quick here after all that. We're going to do this in draw, and we're going to just do that temporarily just to show what's going on, and then after that we will we'll delete that code. So let's draw a grid. We've seen how to do this before. We're going to write first a for loop that's going to count here in increments of 20, and then another inside of it we're going to nest a second for loop. This one will use the y variable to count. Okay. And then inside this one we're going to draw a little box using x and y and 20 by 20, and that should fill our window with a grid. Okay. Now, in addition to doing this, what we're going to do is we are going to use this xy coordinate, and we're going to sample a Perlin noise space, except instead of doing it in 1 dimension, we're going to do it in 2 dimension. So we're going to create a variable, let's call it n. That's going to be our noise value. We're going to use the noise function, and the noise function can take 2 parameters. It can take an xy, and now all of a sudden we're looking at a 2D space instead of a straight line. And we're going to use that as our noise value. And then we're going to use this as a fill, okay, just so we can see it. So the fill here, a noise is going to be always between 0 and 1. So let's just quickly multiply 255 by n, turn off the stroke, and that is going to give us a grid that looks something like this. Okay? Now this is some Perlin noise like rather zoomed out, so it looks pretty noisy. So Perlin noise is always a little bit more interesting once we kind of zoom into the space and get like smoother variation from one neighbor to the next. So what we're going to do is we're going to add a zoom setting to our GUI here. And let's go with let's start with a number like 0.1, and we will multiply x and y by this zoom setting. So in effect, we're kind of like zooming in by multiplying by a small number. And then finally, this is what it's going to look like. And let's add it to our GUI so we can play with it and see what it does. We're going to add to settings. We're going to add zoom. And maybe that goes from this range. Okay, we can always tweak it later if we find the range doesn't work for us. So as I make this number smaller, you see that we're going to be zooming into this Perlin landscape. And the cool thing, again, about Perlin noise is that from one tile to the next in this landscape, in fact, let's go like even more zoomed in, just so we can get like much smoother. From one tile to the next in this landscape, and then here I'm just playing with the settings here. 0.1, maybe that was a little too much, so let's go 0.05. So we can see a little bit better what's happening. Okay, and have a little bit more wiggle room here. So from one section to the next in all direction, we have these smooth peaks and valleys. That's what Perlin noise does. All right, so what does it have to do with, does this have to do with vectors? Well, one thing we could do is we could say, take this noise value, right, which is just a number between 0 and 1 in each tile, and instead of mapping it to a color, we're going to create a small little vector. Okay, and we're going to rotate that vector based on the noise. So let's see what that would look like. We're going to create a vector. We're going to it's going to be a small vector. So just let's say 1, 0. So just like a little line pointing to the right here. Instead of setting a fill, okay, we're going to take this vector, we're going to rotate it by n times 2 pi. Remember, 2 pi in radians is 360 degrees, okay, in case you need to brush up on that. So we're going to rotate that vector, and then we're going to draw a line representing each vector inside each cell. So to do that, we're going to have to use push and pop, and then a translate here. We're going to translate to x and y. Then we'll draw a line that's going to go from 0, 0, and just like in the previous example we did, a 1 pixel long vector is really, really hard to see. So we're going to cheat a bit, and we're going to just multiply these by 20. Okay. Vx and Vy, the X and Y coordinate. We're going to multiply by 20. Just so we can see them, and they basically fill the space available, but in reality, these vectors, remember, they're going to be tiny. Or I suppose I could have made that vector 20 by 0 as well. That would work. So here it's hard to see what the pattern is, but if we zoom into the Perlin noise space, you're going to start to see what I'm talking about. Now we can see it just a little bit better, right? So as we get closer into the noise space, we can see that because values vary smoothly from one position to the next, right? We're going to get these interesting kind of layered, these interesting kind of patterns of rotation. Right? So imagine our agents that we're creating, as they move through this field, we're going to look under their feet and figure out what is the vector that's there in the Perlin noise landscape, and use that to give them a nudge. Use that to apply a force to their velocity so that they move in that direction instead of just randomly moving everywhere. Okay, so that's kind of the basic idea. So let's apply this to our program over here. Just to keep things tidy, kind of the way we've been doing it, we're going to create a little function here. Let's call it Perlin field. Okay? And the input will be an agent. And the goal of that function, let's call it here, Perlin field agent, is going to be to apply a force to that agent based on this Perlin field under their feet. So up here, we're just drawing the entire space of possibilities, right? But down here, all we have to do is use the agent's coordinate, right? And create this vector over here, rotate it, and then apply it as a force. So I'm going to copy these lines just to save myself a little bit of typing here. And the only difference is now instead of x, we're going to say agent.position.x. So this is the location of our agent. Agent.position.y. Sorry, this line is getting a little cut off because it's a bit long. Then we'll create our little tiny vector, right? 1.0 vector. We're going to rotate it. Let's fix our indentation here. Let's not be totally lazy. And then we will apply this as a force on our agent. Okay. So that's going to be our Perlin field behavior. And woo, pretty cool. Now you saw those guys that just went flying all over the place. If I create more objects, right now they fly through this field. When we're zoomed out like this, it's hard to see, but as I'm getting a little closer, if I make the field a little easier to see, and if we maybe reduce the friction a bit, you're going to see that the agents, let's reduce the friction to 8, right? They're following this Perlin field, right? As I create them, they're following the natural wave that's created by the Perlin noise. And that gives us some like very interesting organic motion, interesting behaviors that we can really tweak, right? This kind of a combination of how much we're zoomed, right, to see how chaotic it gets, how much friction we're applying. If there's less friction, of course, they move much quicker through that system. But this is a really fun way to create really intricate movement patterns that are organic looking because they're built on top of Perlin noise. Okay? Very, very cool. Now we don't actually need all these lines right there in the background. This was just to show, just to demonstrate. I'm going to comment this out for now. I'm going to take that out, right? So these lines don't need to be there. We just need to know, we can zoom in. This is now like our objects are moving in this Perlin field, right? Now you may notice one thing interesting here. There's a lot of just left motion, right? Everything seems to be like moving to the left. I mean, sometimes up, sometimes down, but never to the right. Why that is because Perlin noise, even though it's random across the range, right? Where were we? Over here. Even though Perlin noise is random across the range, on average, it tends to kind of cluster around the middle. So it rarely gets to the extremities. So right now we're saying multiply this number. We could use map here as well, but because it's already 0 to 1, it's easy to multiply. We're just multiplying by a full 360. So we're not always getting the full 360. We're getting like kind of more of a pie like this of options. So if we wanted to have more variety, we could simply just like multiply this. Maybe we go like 720, like 2 full circles. Like, let's see what that would look like. I'm going to tweak these again. So now it's a little bit more unpredictable, right? So again, these are parameters of the system that we can play with to sort of sculpt and shape this behavior and get it to do what we want it to do. So now they're kind of going in more directions, just because now the noise is taking us around a little bit more of a range of angles. Okay, so that could be something interesting. The other thing I want to point out, again, remember, so much potential for a drawing machine. Let's get rid of our background here real quick. Very cool. Maybe we bring back the stroke affected by the life so that they fade out. Maybe we make these squares actually like really tiny. Nice. Maybe we'll like reduce the friction, reduce the zoom level a little bit more, right? Now I can kind of like draw on this space. We could really play with this, have some fun. You could have some key presses that clear the background, because when we're tinkering with the settings here, we're actually launching some new agents. But really, really cool. So many possibilities. And obviously, even though, as we talked about in class, this Perlin noise is kind of very much of a cliche in the generative art genre or style, it's still, I think, it's got a lot of potential, because you can, you're the one who decides how you sculpt it, what you use it for. And it's just a lot of fun to play with these noise fields and see what kind of drawings they can create. So, all right, let's go back to having a background here. And we'll do a quick little recap and then call it a day. Where's my background? Up here. All right, very cool. Even with these small little guys here, we'll increase the friction, maybe increase the zoom level. So all kinds of really nice behaviors. Now that we don't have the background anymore, it's more evocative of, maybe some insects flowing around and so forth. And the beauty of it is that it's very, very simple to program, because we're mostly just relying on the noise to do the heavy lifting of the organic motion. So really cool. I could play with this all day. All right, so let's recap. So we took the concept of our agent, right? And remember, we could call this anything. It doesn't have that much agency right now, but I just like the word. This could be, we could think of it as a particle, as a moving thing, like it's just an object in our program. And we defined it as these three vector attributes that allow us to program this kind of very simple physics-inspired motion framework. And then we've taken that agent concept, created a bunch of them by creating an array, right? Adding lots and lots of agents. And then from there, we've added a force to them so that we can animate their motion over time using Perlin noise that we talked about next week. All right. So that's it for this lesson. Just play around with this, with the program, experiment a little bit. If there's other parameters, you might want to add how much nudging in the beginning, how much the lifespan of individual particles, how much alpha value, right? You can always start to develop this interface over here and give yourself different things that you can tweak to really start. I really think of these spaces as sculpting in many ways, even though we're coding, right? We have the space of raw possibilities, and as a generative artist, we're kind of carving away, chipping away at this space until we get something we're happy with. So anyways, I'm going to stop ranting. I'll see you next week. Take care.